So this talk is all about chips. Okay, I thought you were going to talk about chips too, but I know you work on so many different things, mostly about chips. I have some other slides. So I just learned I will need to supposed to give a talk this morning last night. But I have slides, so I will go through them. So we are obviously. I mean, I was at another conference or later. Yeah. So I was at another conference called AI for X. So people are using AI for material discovery, drug discovery. Everybody there is using this, right? Using cloud, using NVIDIA chips, right? So this is the latest NVIDIA chips, right? So it's a Blackwell 200, right? So this is a so-called super chip because it's so big that you can't fabricate it in one run. It's too big that it's bigger than the mask. You have to tile two chips together, and you have some other chips on top. So it's really a big package, but they call it a super chip. So this is basically what powers the data centers every day, and people can't get enough of that, right? So I use this in my class. I ask my students to guess how much this chip will cost. Anybody want to guess?
What's the process technology and what's the area?
This is like
3.
I don't think this one is 3 yet. This one is a 4 nanometer. Yeah. Next one is 3. This one is 4. But this is like bigger than the mask, right? So the full mask is like maybe 55 by whatever 60. Right? This is bigger than the reticle. Okay.
So say 1,000 square millimeter.
1,000 square.
Is 30.
Including HBM or not?
Yeah,
Not HBM.
No, you could.
HBM is
No, these are HBM.
So your questions on the cost is including the HBM?
I'll include everything. Yes, the package.
Including everything.
Yeah. Sell just the chip.
I would say about $200.
That's the actual cost. Yes.
About 40K.
Yeah, you are close.
Not for for the system, for the chip, yes.
It's about 60K, and you have to beg Jensen to get your hand on this chip, right? And it runs, obviously it's very powerful. It's 10 petaflops, right? 10 to the power of 16 flops at IP8, and it consumes 1,200 watts, right? So this is basically the thing you can only put in data centers, and only the biggest players can afford, right? I mean, only the Microsofts, and Microsoft, in fact, they stopped paying dividends. They lay off people so they can buy enough of this, right? But this is obviously not what we are targeting, because we are not targeting data centers. We are targeting very efficient chips that can run with basically at the edge, right? So it has to be based on a different mechanism, because even these very powerful chips, they have problems. And I think this audience knows really well. But the problem is that they have separate memory and logic, right? So even with HBM, it alleviates the problem, but it doesn't solve the problem. So your memory and logic are separated, so that theoretically you get 10 petaflops, but which actually you can't get it when you do model training. You can get close to it, close to your theoretical limit. But when you do inference at the edge, yes. Yeah, I'm trying. I'm using most of it. Yeah. Yeah, I want to point to the screen, but I'll try. Yeah.
Just look at your laptop. That's the trick.
Okay.
Just look at your laptop.
So if you are doing model training, you can use basically so-called, you can reuse the data. You load the data once from the DRAM, and you can use it for many times. So that's why people can get close to the theoretical limit. But if you are doing real-time inference like humans do, we interact with our environment, you load the data once, that's your model from your memory, and you use it only once. So you can't reuse the data, or most of the time you can't reuse the data. So then your utilization is here. So a lot of applications for real-time inference, their utilization is less than 10% or even 1%. So you have all this chip area, all this processing power, but you can't use it. Okay, so that's basically the memory bottleneck we all know very well, right? So that's why here, this audience, we are working on neuromorphic computing. So I've been working on in this field since 2008. But in my view, right, I'm a hardware person. So we take a two-step approach. So obviously, Brain offers many very nice properties, right? Many of them. So I want to put them in two categories. One is that your organization is different. Our organization is different. So instead of having separate memory and logic, we have memory and logic merged together, right? That's computing memory. Use the memory cells to perform logic. So that's the first step. That step, I think, it's closer to large-scale deployment, I would argue. So, I've spent a lot of time working on building larger scale systems and actually building a software ecosystem to support these kind of chips, the so-called computing memory systems. They are obviously neural-inspired, but they don't offer all the properties. They don't offer spiking. They are not based on fully analog computation. So they are basically the second step. So then you can introduce more biophysical dynamics, spiking, and all the nicer features, but they are a little harder to implement, both on the algorithm side and on the hardware side, in my opinion. So that's why I feel it may be interesting or useful to take two steps, right? So you do computing memory first, you build the infrastructure, you convince people, because here we all understand the importance of that, but people look at the models, they are all deep neural networks, they are all NVIDIA-based systems, right? So you have to convince people this alternative approach is real. It actually can be scalable. Then you can also introduce more features. Okay. So I'll discuss the first step first. So basically just computing memory. So I'll try to go through it quickly. So I'm also a device person, so we work on this device called memory star or resistive random access memory. So it's basically a resistor. So you can build a resistor with anything with 2 electrodes and a film, right? But the resistance can be changed. So in this case, we change the resistance by moving ions inside your the film in between your 2 electrodes. So there are different types. I will not have time to go through them. But the idea is that when you program the cell, you actually change the ion distribution. So you can, in some sense, you can argue it's almost like a battery, but a really, really tiny battery. But instead of storing energy, the ion distribution changes the electrical property. Yeah.
I just want to comment on you had something on the previous slide that much like neurons, which compute with ions,
yes,
your system also computes with ions.
Yes.
You had this here, but you didn't talk about it.
I will have a slide discussing this in more detail. Yeah. So this is just an overview. Exactly. Thanks for pointing out. So exactly. So these ions are very useful. Obviously, training the ion dynamics actually can be aligned with the dynamics in the neurons and synapses. But from a device point of view, you can program them, you can control them really well. So you can build the devices, you can also model them. So this is one model we developed. It shows the different distribution of the ions. In this case, the ions are oxygen ions in an oxide. So the different color represents the ion concentration. So higher, darker color means higher concentration. Okay. So by applying a voltage, you can change the ion concentration in this film and then change the conductance. So it starts with a low conductance, then at a high enough voltage, it changes to a high conductance. Then it can be switched back. So you can change that. So it's really a dynamic device. So when you program, you change the ion, you move the ion, you drive the ion dynamically. As a memory, we don't consider them as a dynamic device. So we consider them as a device with many resistant states. So the idea is that when you drive ions, right, this is a very simple model. So when you drive the ions, they have an activation energy, right? So normally they are stuck at a location. So at room temperature, when you don't apply a large field, you get one state. It's very stable. It can be stable for years, so you can use it as memory. But when you drive it, when you apply a programming voltage, you tilt this potential because you apply a Coulomb potential, you have an electric field. So your Coulomb potential is combined with your electrochemical potential. So it actually tilts this potential. And now the ion sees a lower barrier because instead of seeing this original barrier, now it sees the lower barrier. So now it can be excited through thermal excitation and move to a new state. Okay. So
But there's no such thing as like a valence and conduction band for these ions, is there?
No, they are not. These are not semiconductors. They are not periodics, right?
None of them. There is a lowering of the energy barrier. They still have to be excited to some state to get over the barrier.
Yes, yeah. It's some energy, right? So it's basically there's always a probability for this ion to jump over the barrier. But if the barrier is high, if you look at this,
quantum mechanically.
Yeah, no, the quantum mechanics, just anything is the first principle, is a first order thermodynamic process. So any chemical process.
Suggests that there is a distribution in a conduction band, kind of.
It's not conduction band, but the distribution of the thermal energy of the ions, you can consider, right? So it's not it's kind of like a conduction band, but conduction band is one example of this, right?
I mean, and essentially there you have the Arrhenius law.
Yeah.
It's really the chemical.
Exactly.
Right,
Yeah.
chemical reaction.
So
yes.
consider that Boltzmann distribution for the ions, right? So yeah, so some can jump over, but it's exponentially hard. But when you apply electric field, you reduce this barrier height. You can derive all the equations. Its barrier height is now reduced from this one by the applied electric field. Okay, so now, essentially, from figuratively, you reduce the barrier height. So now you can exponentially accelerate this process. Okay, so that's why you can program it within nanoseconds. But once you stop the programming voltage, you can use a small voltage to probe the state, and it can actually be stable for years. So this is we developed a model. We did a lot of experiments to obviously to show this is actually first order, right? There's always deviation, but
and the numbers there are the size of the device. The numbers in your plot there.
Yeah, the numbers are. This is actually depends on the independent of area, but depend on the thickness.
The thickness of your device.
Yes. So you can cycle them for millions or tens of millions of cycles. So they are very good memory devices. So for memory, you are only interested in two states, on and off. But for computing, you can actually leverage multiple states. You can leverage dynamic process, as we'll see later. So, so the first implementation is that you can just use them as a memory device. Then you build this so-called crossbar structure. So at each cross point, you have one device. And so you can use them as a memory, but you can also use them to do computing directly through the memory, because you can use their conductive property. So apply a voltage, you drive through this resistor, you get a current. That's just Ohm's law. And then you have an array of voltage coming in, you get this current out. That's a vector input multiplied by the conductance vector. That's Kirchhoff's current law. So you can use this physics to do computing, but here the physics is very simple. It's just Ohm's law and Kirchhoff's current law. And you treat them as static devices with different conductance values. So I programmed into 1 or 0. So I programmed the weights into the conductance values. Okay. So when in computing, I'm just doing kind of like this probing operation of kind of read, but instead of reading one cell, I'm actually reading the vector output from all the cells. So mathematically, you are doing this vector matrix multiplication. As we know, it's the most important application in the neural networks, right? And you can get this in one operation because you get total vector output from a single operation. Okay. So you can also get you can feed the signal forward. You can also feed the signal backward. So you can actually feed your activation function backward through the transpose of the weight and reconstruct the original input. Okay, so you can do this for training to do back propagation, or you can use this apply some math to use this to construct a recurrent network, a simple recurrent network. All right. So over the years, we built multiple prototypes to gradually increase the functionality, starting from the chips with external functions, then with everything fully integrated on chip. So these are the memory star crossbar arrays. These are the CMOS circuits that performs, some arithmetics and some routing, but all the matrix multiplication are performed in the crossbars. Okay.
And just one comment. So this presumably is very easy to make because all you need is basically two wires to cross each other and an oxide or whatever. Is that one of the advantages? It's
very easy to make for a single device, but if you want to make it very reliably, it requires a lot of engineering, right? Yeah. So, but it's easy. It's relatively easy, right? So you can integrate it in the so-called backend of the line. For example, integrate on top of CMOS layer. So this is very clear. So these are the crossbars. These are the so-called vias, metal vias that go down to the CMOS underneath. So you can, I have a startup offering this commercially, but also you can, TSMC and Samsung, they also offer this as our macros. You can actually directly get them from the fab at 40 nanometer and 22 nanometer. They will have it available at 12 nanometer very soon.
Yeah,
the context as well, that 2019 chip was well before anyone commercially was making these IPs available, right?
Yeah,
And that was the first fully integrated memory system.
Yes, yeah, this is like, obviously, we're fortunate we're one of the first to actually implement a lot of those concepts.
After all this talk and all these years of working on this stuff, I haven't seen a single Mr. chip here at the workshop. An actual hardware chip that anybody's worked with.
Oh, I should have.
Single one.
I should have brought some, but I was going to Singapore first. I don't want to get in trouble at
Never seen a single like that.
No, let me show you. Let me show you a photo.
Next year, we'll make sure we have one.
No. We have
The
one.
hardware group will bring one next year.
Yeah, we have a lot. I will show you photos, but I don't want to get in trouble at the customs because I'm actually flying.
Oh, yeah, that's, yes.
I'm not flying here directly, so I just came back from Singapore. So this is like a simple two-layer network we built on this device, and it's actual chip, right? This is the actual chip photo, so it's not PowerPoint imagination. So, but there's still a lot of challenge, right? So you are doing this analog summation. There's device non-idealities. You are also because analog, you have limited precision. So also your array is not as large as your network layer. So you have to divide it into smaller arrays. You have to map a larger layer into multiple arrays and combine the sums together. So there's this quantization effects. There's device non-ideality effects, quantization, your device has off ratio limitations. So then you have to consider this. And the other thing you have to consider is that because data computing memory, we're not utilizing the dynamics. So mostly they are, we use them to map more conventional networks. So they have very large size, hundreds of megabytes, right? How do you map these hundreds of megabytes or at least tens of megabytes on the smaller chips? So that's another problem because you don't want the width to go off chip because then that completely defeats the purpose. You want to map the whole model on your chip. So that's another challenge. How do we make sure we have enough memory to map the complete model? Okay. The first one, you can kind of address that through this quantization of device-aware training or variation-aware training. So people call them VAT, variation-aware training. So I will not go into the details, but basically you can have different levels of detail. So the more hardware detail you introduce your model during training, the better the model can handle these hardware non-idealities. But there are some tricks on how to do that. So I have a recent paper that will be published very soon discussing some of the tricks you can deploy. But anyway, the idea is that by introducing these hardware details, these non-idealities, during training, the model can more or less adopt handle this hardware non-ideality. So this like what we are showing in this paper. So for simple model, they don't care. But for this more complex models, you have to increase more.
What does that show? Accuracy on the vertical axis?
Accuracy on the vertical axis. So
CIFAR10 and
yeah. So CIFAR10 MNIST, obviously very simple model. This is a CIFAR10. This is a CIFAR10 with VGG, which is more. It's a dumber model, so a lot of redundancies. So this is a more compact model, ResNet-based model. So a lot more compact. So a lot more sensitive to the device variabilities. Okay.
then the different. I can't read it.
Yeah.
The difference between device-aware and tile.
Yeah.
That.
Different levels of hardware information you introduce to the model during training. Okay, so the more information, the more accurately you can describe your hardware during training, the model can handle this non-ideality better. Okay.
But white floating point is 10%.
So this is not doing anything. This is just mapping the floating point. Okay, not doing any. So this is a label. That means this is running the floating point model as is. Okay, so this is just doing inference. This is not showing. There's a lot more. This is just showing training inference results for the model trained with different considerations.
But what does tiled mean? Means you have redundancy or something?
No, tiled means that if you have a large layer, right? So your layer is say is 10K by 10K. Your crossbar is only 128 by 128. You need to map this into say 100 by 100 of those arrays. Okay. So then you have this partial quantization effects because after each layer, you lose some information because you do some quantization, you lose some information. So if you don't consider this, the model will fail.
So timing overlap a little bit, or
No, they don't overlap. They don't overlap.
Oh, I
Yeah.
see.
So it's just how you do the mapping, right? You map.
I see.
Yeah. So it's just granularity of
it's
the.
an algorithm that you develop and read about.
Yeah. So anyway, so this is not as important. You can read the results in the papers. This is showing some. This is actually another approach showing how do we deal with the limited capacity. So for limited capacity, you can obviously do pruning. So we are not advocating this. We advocate for better models. But if you have to do pruning for this computing memory, you can't use this so-called unstructured pruning because you want to feed. For example, this is your crossbar. Okay, you can't feed because you are feeding the vector at once, right? So all the vectors are fed to all the kernels. The kernels are in the vertical direction. So they have to be the same because if I do this unstructured pruning, so every kernel has a different shape. I only keep this one. It doesn't work because they are seeing the same input. So you have to do a structured pruning. So the finer the structure, it turns out the better the performance. So again, there are some tricks. You can use this general so-called shape level. So it's array level essentially. But then because you are doing some sharing in the columns, you can actually get finer grain at the array level. So anyway, so the results are shown here. So you can get a compression ratio about 10 without losing much performance if you do proper pruning. Okay, so this is just the gist of it. The other trick is that you can do this so-called tensor decomposition, right? The tensor decomposition is now very widely used. So because people do so-called LoRa on these large language models, it's basically the idea is that you have a large weight matrix and you can decompose it into the product of two smaller tensors, okay, or multiple smaller tensors. Then your stored weights will be much smaller. But the problem is that then you need to do more computation. So you have smaller weights, but you need to actually do a lot more computation. So in this paper, my student came up with a way to smartly reuse the partial computation results. So you actually don't end up with more costs than you save. So again, like there's a lot of math involved. I will not go into the details, but the idea is that you can actually preserve the precision and get a reasonable compression ratio and actually get a reduced computation. Okay. So there's trick. The whole idea of this is that there's challenges, but there are approaches, right? Not just my group, and people are actively working on to address this challenge, right? So what I want to discuss is another another factor we have to address for this kind of a system to be very widely useful is that the models are obviously getting more complex. If you look at, I mean, it's obviously extremely simple, but if you look at MobileNet, right? It's a complex model to work on, for example, ImageNet, right? So it has 2 million parameters, but it's actually a very simple structure. It just keeps going forward. So these are different dots are different layers, essentially, okay? They just keep going forward. But if
Is the vertical axis here?
no vertical axis,
There's no
it's just graph,
It's a
okay?
graph.
Yeah. So if you look at the ResNet, it has these branches, okay? Because this is actually one of the concepts introduced is skip layer. So the skip connections makes the model actually a lot more efficient in training. So you see it gets a lot more complex. So your data flow becomes more complex. So assuming you map all the different layers on your chip, different parts of the layer map different parts of the model. How do you move the output from this layer to the other layer, right? You can obviously just use switches, but it turned out that it's not very, it's getting really complex to program when your model gets
Colors mean here?
The colors just mean different layers.
Different layers.
Yeah.
And essentially MobileNet 1, you can pipeline everything.
Right.
It's just a pipeline, so you get very efficient, very easy implementation, but everything else you cannot.
Exactly. So how do you actually address this connection, right? So I have this model output. You need to go through this branch and go through this branch, and they merge together and go through here, right? So how do you make sure all your data passing through all your blocks correctly and very efficiently too? You can't have a huge memory and collect all the intermediate results. You don't have that luxury on chip. So that's actually you don't notice this challenge until you start working on these bigger models, right? So obviously, Andrea knows this really well. So the simple approach is that you can just build these files, you connect them together with a bus. But then the bus quickly become overloaded because your bus it's kind of like a von Neumann concept, right? You don't have a memory and logic separated, but now all your data want to share the same bus. You have a bottleneck. Your bus, if it's very long, then it can't be very wide. If it's very wide, it's then really short. You can't have both very wide and long buses because then it consumes too much power and area. So the initial chips we built are all using a bus here, right? It works for smaller models, but it actually completely fails. It can work, but the efficiency becomes extremely low for this more complex model. So you have to come up with a way to address this data flow problem, more than just computing problem. Okay, so to this end, because this actually becomes more, I would say, beyond what my students want to handle because they want to publish papers in this. And if we look at the software layer, they don't want. It's harder for them to publish papers. So and also this scaling seemed to be better suited for a company to do. So I started another startup called MemoryX. So we actually spent a lot of time developing the approaches to make the data flow smooth on chip. Okay, so you can actually read the architecture details on the website. So that's a white paper discussing all the chips we employ to actually make these larger models work. So then we developed the whole suite of software. So it's hardware is not enough. You have to have a very easy to use software, otherwise people won't adopt, right? So we have the compilers that map any model on this data flow architecture. So data flow means that you are not loading instructions, your weights are stationary, you're just flowing data from one place to the next, right? So we developed it's completely different compiler. You can't use the existing commercial compilers. So you have to use develop your own compiler. We have to develop APIs, the drivers, and all the higher level application layer stuff. So people can actually use the chip. Okay, so it's a lot more effort than we thought, but it's really, really useful, I think. So these are actual chips. Okay, so it's a third generation. So the first generation was already done in 2020. The second one was 2021. Third one was 2023, and it actually gets another evolution last year. Now it's actually fully qualified and completely in high volume production. Okay, so this is 12 nanometers TSMC, and you can actually buy it from Amazon. Now you go to Amazon and search, you can actually buy it if you want. Okay.
And you're using the membristors in the TSMC technology, or you?
Not this version, because this is 12. They don't have 12.
7, yes.
So what is the memory? SRAM here?
This is SRAM, but the same concept. Okay, so the density is lower.
Perfect.
Yeah.
Perfect SRAM.
Yeah. So
But anyway, this is software architecture.
Yeah.
Let me just ask a stupid question here. Most of those models show there are CNNs where you have small kernels that are repeated over and over. How do you do CNNs in this weight stationary architecture? Do you have to have many copies of the same weights?
no. So
It's typical, so it's very different than a typical NPU you have in a smartphone, right?
yeah. So let me first clarify the first question. So this is the first two were based on memory stars. Okay, so it's 40 nanometer and 22 nanometer. They actually work not as well because they are slower. Okay, so then we want to move faster because this is like a accelerator. You really need to get the performance and
Throughput,
yeah. So they don't have it. So that's why we use SRAM, but same architecture, same software. So for CNN, it's hard. It's harder because you have to have yeah. So that's why I have another slide. So CNN is not perfectly suited for computing memory. Okay, but that's what it is. Okay, so
what's the power that you consume with?
Yeah. So this is a comparison. So this is the one we benchmark with. Okay, this is like a 4060. It's a year old. They have 4070. Hopefully you can buy very soon. But this is like still the data available is 4060. So we compare the performance of those two. we look at the raw performance, not like on the same model, the raw performance, raw throughput. This is our system is 2x faster. Okay, we're not normalized against the tops. This one has 200 tops. This one has 20 tops. But we're actually 2x faster because we get rid of the memory bottleneck, just the raw performance. Same models, we don't tweak the model, exact same model.
So what's your bit density? How many gigabits per millimeter square?
Yeah, so I need to recalculate, but this is basically like
6 transistor SRAM?
Yeah, this is 60 SRAM. So we have half of the chip area is SRAM essentially, because that's why it's a lower density, right? So each chip has about 10 megabytes.
Oh, 10 only?
Yeah, 10
Oh,
megabytes.
I see.
Yeah.
So what was the power for the 4060 versus the?
Yeah. So the 4060 is 100 watts. This one is like about normally when it's at full speed, we run it at 1 gigahertz. It's about 10 watts, but in general, it's less than 5 watts total.
Yeah.
But can you map the same models?
Yes.
Like model size? I mean, how can you? I mean,
No, it has to fit. So we mapped about 1,000 model. You can actually go to web page, see all the models. So we don't call it model zoo in the sense that model zoo people normally tweak the model. So these are all open source models directly mapped. Okay. So as long as you can fit. So one module you can fit about 40 megabytes of weight. Okay. So you can have multiple modules to fit bigger models.
Well, much like the NVIDIA card.
Yeah.
At some point, it has to go.
Right.
How much memory does it have?
Yeah, this one has 4 DRAM. Right. Yeah.
How much DRAM does it have? I think it's 12.
12 gigabytes. Yeah.
4?
4, 8.
Yeah.
Yeah.
So this one is obviously 5 nanometer. I think this is 12. So again, just raw performance as long as you can fit the model is 2x. Okay. So that's just obviously size and power has a lot more advantage.
And you're targeting integer arithmetic for inference?
This is the floating point. So we use
Floating.
yeah. So activation is floating point. Weights are 8 bit. Activation is floating point. Otherwise, you have to do a lot more tweaking. Yeah.
Yes.
Yeah.
But if we want to buy one of those, how much do we pay for that module?
You go to Amazon, you can find Amazon business guy. So I think Amazon right now is 150. Yeah. So you can put it on Raspberry Pi. In fact, we're running a summer camp for high school students. So you can buy a Raspberry Pi. Origin Pi is slightly more powerful. Anything with M.2, you can plug it in and you can run the model.
But you have to have this M2 slot.
You have to have the M.2 slot, but we're very standard, almost.
This is not memory stores, to be clear.
This one is not memory stars, yeah. But if you use our second and first version, they are, yes.
Yeah.
But the same concept, yes.
Because Toby wants memory stores. So.
Oh, yeah, we have the bigger board.
I'm joking.
We have the bigger board, yeah. So yeah, but memory stars can do more, okay? So that's what Andreas was referring to. So previously, we are still in this camp, right? If you look at what's the difference between what a brain does and even if you use computing memory, the accelerator does is that in brain we don't have programs, right? So the system autonomously processes information, and it does that at all levels of the stack. From the molecules will reorganize, the cells will reconnect, and organs and obviously organisms, all the levels respond to the input dynamically, right? Even in a CM accelerator, we rely on algorithms, right? So these things are static. So we program the way so it becomes static. We rely on some instructions. So the only thing that's dynamic is the software, is the program. So that's not ideal. That's why there's a lot more we can learn from the brain, or we can use and utilize from the brain to improve the efficiency. So this is actually a nice review I wrote with Kumar Suhas Kumar and John Paul.
And by the way, if I make a commercial break now, John intends to talk about. Are you going to talk about this hierarchical layer-based approach to? Yeah. So there's a complimentary talk on a couple of days from now by John on the previous slide, the challenges and how to do that.
Excellent. Yeah.
But I'll spend a lot more time on biology, back to bacteria, how it all got started.
Yeah, that's perfect. That's why I come to this conference to learn, right? So we are a device person. We're trying to learn from the findings in biology, right? So to make a simple analogy, right, as Andrea was saying, so in biological system, neuron synapses, the functions we observe, they are effects, right? That's not the cause. What's causing the functions, what leads to the functions are internal ion processes, right? Ionic processes or molecular processes. So in memory store, you have these ionic processes. They are governed by ionic dynamics, thermodynamics, and electrical dynamics. So the idea is that we can leverage the ionic dynamics or electronic and thermodynamics. We can go down to the fundamental equations and try to align those equations to the equations people derived from biology and see if we can actually implement the functions more natively rather than based on some algorithm. So that's basically the next level we want to get into, right? So these are the memory star equations. So they have so-called several state variables. Normally, we just consider the conductance, the W, but you can also have temperature as your state variable, right? So this is what we call second-order memory star. So you have two different interdependent variables, and temperature change actually is short-term. The conductance change may be long-term or short-term, but temperature is short-term. So this actually turned out to have some really nice biological analog. Because in biology, at least in some models, for example, BCM model we follow, the calcium dynamics, you have some short-term dynamics, and for example, the post-synaptic membrane potential, it will increase and decay. And this overlap between the input and output, the effects of the short-term dynamics leads to the long-term change.
What is this capital T, temperature?
Temperature, actual temperature, yes.
So D temperature, D time is some function of
Yes.
the power.
Yeah, because it depends on whether you apply voltage or not. And when you apply voltage, before moving ions, you are heating up the device somewhat, okay? Then when you remove the voltage, the temperature will decay, but it doesn't decay instantaneously, right? And when you move the ions, if you change the conductivity, you change the temperature profile, and you have a different temperature decay. So this is really intercoupled, right? Very complex dynamics.
But also you could put them and restore an electron microscope and heat it up with the electron beam.
Yes, you can see that, right? Yes.
You can see that.
You can control the temperature
Yes.
externally, right? Yeah, so you can model this. We can model this for example, as I said earlier, you can heat up, you can apply one pulse. The pulse doesn't have enough voltage to drive the ions, but it can create temperature rise, right? Temperature increase and temperature decay. Another pulse comes in, and if the temperature already decays to the base temperature, nothing will happen. But if they are close, they don't overlap, they are close, you have enough temperature rise, now you can actually drive the ions. So that's this is basically what we are trying to get, is that you can get this autonomous response from the devices, right? Each pulse, each spike doesn't cause a change, but the relative timing, if they are just right, they actually can cause a conductance change or synaptic change. So with this, you can implement timing-based rules natively, right? So you don't have to yes.
So what's the time constant for this?
Yeah, very short. That's the thing. So
sure.
Microsecond.
yes.
Is it?
Microsecond.
Microsecond.
Yeah. So we are really trying hard to try to increase the time constant because it's misaligned with the biology, right? But some devices can have, so that's one. So this one.
But just philosophically, why do you care that it's faster than biology?
That's the matter.
Yeah. You
Like,
actually
why
want
do
to
you want it to go slow when you want it to be?
Depends on the application, So if some applications, we have collaborators want to connect it to a biological network. For example, the idea is that.
Okay, I understand.
Yeah. So
the old philosophy of matching the scales.
Yeah.
So that's why they have buffers. So you could have biology run rates and the chip runs at a different rate.
If you can do it without buffer, that's supposedly is more ideal, right?
But this is brilliant, I think, because it uses the physics to learn,
Yeah.
In this case, STDP
Well, just by melting material, right?
But
Yeah.
this is basically just from Mazal heating of the material with the pulses, like.
Internal
the
draw
valve
heating.
heating.
Yeah, draw heating. Yes. So you can control that. So this is another paper we did. So you can change the device structure. You can control how much. Basically, you can control the heat dissipation. So you can get different. You can get different STDP behavior and change the effectiveness of the STDP and get a different time constant.
And the simulations there, TCAT, I mean, you're using the.
Yeah. So it's basically,
This
what's the?
commercial, whatever. they come with,
What some sort of model,
Yeah.
So what is the fastest time constant you can get?
Fastest is less than 100 nanoseconds. Yeah. We try to slow it down, but we because faster is very hard to measure as well.
Yes.
Yeah. So that's what try to get. So one of the directions is potentially to connect the biological network to this memory star network. So this is a simulation. So all previously were experiments. This is simulation because the time are not aligned, right? It's misaligned. So this is basically using I forgot the model structure. So basically simulated biological network. So the idea is that can you use this artificial memory star network to learn the connectivity in your simulated
Looks like
biological?
reservoir computing.
This is not reservoir computing yet.
It's not.
No, this is based on HTTP long-term memory. Okay.
Oh, I see.
So it's long-term. So reservoir doesn't have learning. This one has learning. So so the idea is that we always do is that this is a neuron. They have like a connectivity. Then you just feed random noise to the neurons. Then they will spike. So it doesn't do any function, but because of the connectivity, the spikes have some hidden information in it. So the question is, can you decode this hidden information and eventually construct the connectivity in your biological neural network, simulated biological neural network? Yes.
So in order for this temperature thing to work, you need to drive it with quite some energy, I guess. And
yeah.
So this is more than reading. So what's the ratio there?
Yeah. So it's even read you can heat it up slightly, right? So normally we program it say at 1.7 volt, and for this we use say 1.2 volt to do
read.
To do the no read is like 0.5 for the SDDP type of thing with 1.2. Yeah. So it's not enough to program it, but it gives you enough heat, and when the heat reaches enough temperature due to the overlap, this 1.2 is enough to move the ion.
The heat is not explicit. The heat is in the timing.
Yeah.
But what is the energy like need for reading versus writing? That's
reading is it all depends on the conductance, right? So it all depends on the conductance. Yeah. So these are like definitely less than picojoules. But I have to look at the numbers. Yeah. You can easily do the calculation if you know the conductance.
But also, eventually, you could use 1T, 1R, and then that would reduce the readout because now you'd be reading not conductance but current.
Right. Yeah.
So what material is this exactly? It's a solid state electrolyte?
This is a tungsten oxide. Sorry, tantalum oxide.
This is a solid state.
Run of the mill,
yeah, tantalum oxide. So in fact, this is actually what people use in the commercial fabs too. Tantalum oxide. Yeah.
And is it the same material with the temperature dependent?
Yeah. This is a tantalum oxide. Yes, I have the TEM.
So what type of ions are there that are so dependent on the temperature?
No, these are oxygen ions. They are all dependent on temperature.
All depend.
It's a somewhat process. Yeah. They all depend. It's a first order reaction, right? So it's all. Yes.
What density of the heat can you achieve the temperature so the temperature does not diffuse?
Yeah, this is a good question. So we haven't done that much study to look at, but it's completely inside. So we have done simulation, right? So here you can actually look at how much temperature diffused it, but we haven't done the experiment to verify this. So this is a temperature profile. This is a temperature profile. I should have the this is I don't have the scale. Yeah, but I don't have. I don't want to make up number, but it's all in the papers. Right?
So how much does the temperature change up and down?
A few hundred degrees.
100 degrees.
Yeah, hundreds of degrees.
Well, then it's huge.
Yeah, hundreds of
It's
degrees.
exponential.
Yeah,
It's huge.
yeah.
Localized.
Yeah, it's localized. Look at that.
And then it cools in microseconds.
Oh yeah. I mean, it's very fast because you're like it's still in a bus of like
Well, there, you can read there, 300 to 400.
Yeah.
They're tiny devices and they're surrounded by big,
Yeah.
with very conductive.
Yeah.
You don't want to dissipate to neighbors, right? It's.
Exactly. So they don't, so far they haven't discovered the neighbor, but we don't know how far, we haven't done experiment to see how close we can peg them. Anyway, so the experiment, I mean, theoretical simulation experiment, show that just by feeding these spikes, right? No algorithm, just feeding the spikes to this memory star with the second order effect that can show the STD behavior, they can actually reconstruct the connectivity in your original network, right? So we did some studies show, like this is basically showing the correlation, have a very strong correlation, and you can study the device variations and the sensitivity. There's different sensitivity and noise in the spikes. So it seems to work pretty well.
So it looks like that network actually is one of these Abbott or Deneuve networks where it actually takes things in a connectivity with learning between the neurons, and then here comes up a sparse representation.
Right. Yeah. So these are the actual connectivities in this simulated network, and this is over time. This connectivity is actually transferred to the biological network just due to the spikes. So this is the SDDP. So we also have this one. You can have longer time constant because some applications want longer. I mean, like this too short. I mean, like microseconds. It's harder to control. That's why we don't have a large array on this because it's hard to control the internal temperature. So we stopped at a few devices. It's really hard to make an array of it. But this type of device I'm going to talk about, you can make large arrays out of them very reliably. So this device, they only have short-term memory. Okay, so basically this is your programming, but then they decay. They just the ions just diffuse. So they diffuse to their base configuration. So they lose the memory. So this is just short-term memory. So with short-term memory, you can't do learning because learning needs to be a long-term, right? So you need to memorize the learned state, right? So you can't do learning, but fortunately, we were struggling to try to find some application. Then my student found out there's actually a group of theory in computer science called reservoir computing, and you know this well. So where they actually rely on the short-term memory, or they call it echo state effect. So the idea is that in a short-term memory device, obviously you can't learn, but you can still convert. You can decode the temporal data, your original temporal spike information in the temporal domain to this new state. For example, this is one device. This is just one device. If I feed the spikes to the device, then depending on the temporal information, temporal configuration of the spikes, the device will end up at a different state. If they are close, the conductance will keep increasing. But if you also have 3 spikes, but this spike is further away, then the device will decay. So the final device state depends on the combination, depending on the combination of all spikes, but not only the number, but also their temporal information. So if you use temporal coded spikes, this code can be converted to the device conductance. Okay, so this is basically showing the device conductance with all 16 different inputs. They can actually be separated.
So can you inhibit this in any way? For example, driving negative?
Inhibit?
Yeah.
When you drive negatively, you accelerate the decay, right? Yeah. We want to utilize it. We want to utilize it because in this reservoir computing concept, you don't use one device, you use a collection of those devices. So this is so-called the reservoir state. So your reservoir state is a collection of all the states of all the memory stars. So if I have not just one spike, right? Suppose you have many neurons, each neuron have a spike chain, then they will excite the reservoir state to collectively to a state, depending on all the neurons spikes. So this state can't be learned, but they represent the input, right? Then you can use the readout. Just by reading out the state, you can get an output. So obviously the question that if it doesn't learn, what's the benefit? Well, there are 2 benefits. The first benefit is that this is a very nonlinear transformation. So you want to detect some original data or you want to compress some original data, the real data is not separable linearly, but after this nonlinear conversion, it can become separable, right? So that's the first. The other one is that you can project it from a low dimensional space to a high dimensional space. There's a lot of benefits of projecting them to a high dimensional space. Again, it makes a data compression feasible, or make the originally non-separable data linearly separable. So your readout is just a linear readout to read out the projected state in this memory in a regular state. So this is a simple test where we converted this row of image into a neuron. So this is not native, natural, but we just test. So you have like 20 rows. You have then we have a collection of memory stars, each receiving a spike corresponding to a row of input. Then you read out the collective state of the memory stars. They can do image classification through training this very small network.
But you have to apply these things over and over again to excite this, or it's basically RC decay, right?
Yeah, it's essentially
Just
RC
like
decay.
an RC decay.
Yes.
So you excite the individual connections. Do you have a network here or something?
We don't have a connected network. These are like separate devices, different nodes. Yes.
There's no fully connected network here.
No fully connected network.
Right.
So they're literally just memristor elements.
Yes.
So you basically have a line of RC decay
Not-
cells.
Not serially connected, independent. It's a collection,
Just like
yeah.
RC decay cells.
Yes.
Excite them.
Yes. You can use RC. You can use exponential.
Some expensive readout.
Readout is very simple. Readout is very cheap. So this readout is a single layer, like say
But it's
20 by 10.
still doing a vector matrix, right? On each one of these single
Right.
rows, right?
Right. Yeah. No. So you have many spikes from a single row. So the memory star state kind of like compresses the many spikes into one state. One memory star converts into one spike. So suppose you have like 20 spikes, right? You have 20 rows, but you have 20 in this
You're
direction.
generating spikes from each row. You're
Yeah.
highlighting rows.
So I'll use another example.
Okay.
Like this is more native. This is more like temporal. So it's really used for temporal information processing, right? So let's say this is like a spoken digit. This is your cochlear model. This is like a frequency channel, right? So your frequency channel, you have many spikes. All of this converts the device into a state. So this is compressed into a state. Then you use a simple readout. This is your readout there, very simple readout, and you can create the output.
But I have to be a little bit skeptical. It's nothing more than a high pass filter feature vector. Right.
I don't know if it's a high pass filter.
Spectral feature vector.
I don't know if it's high pass. It definitely has a but
Yeah, you're excited and decay, right?
Yeah.
That's filtered.
But it's on the weights though, right? So the
yeah,
weights are-
it's not.
These are just the audio features that are then,
Oh, the weights are.
Yeah, it's well, you have to accumulate. You have to be able to accumulate them. So it's not doing the spikes independently. So it's temporarily accumulating them.
And it's non-linear.
Yeah.
And the RC cycle would be linear.
Yeah. So
It's amazing that you can get this high recognition rate from 10 images.
yeah.
A set of sentences from different speakers, etc. And you're saying that you can just project all these strikes.
This is not sentence. This is spoken digit. This is a digit. So 10 digits.
Oh, this is not.
Yeah, it's a digit.
But you
Yeah.
know the sentence
Yeah.
that you-
No, this is basically the same cochlear model, but the actual task is a digit. Yeah. So that's why you have 10. Yeah.
It's given an example of
Yeah.
an audio.
Hey, you shouldn't look at it like that. It's so misleading.
Anyway, it's nice try.
So
So there, when you say logistic regression and training, there you do have fixed weights.
That's just readout.
for the readout,
Train the readout.
for the readout.
The
The training is there.
And how many, so there's fully connected later.
Yeah. So that's the beauty of reservoir computing. But it's not just RC delay. So if it's exponential, it's simpler. So this one is not exactly exponential decay.
Not clear to me how it's different than an exponential decay. Some other fancier nonlinearity.
Exactly. Some fancier nonlinear exponential decay.
Somehow.
Yeah. No. This one is based. It's not somehow you can model the device physics. So this is completely based on the device.
What is the magic recipe that gives it long memory, for instance, compared to RC decay?
No, it's not the magic than RCDK. It's just if it's simple magic RCDK, you lose some performance. It's more the more nonlinear, the better the performance. It's not like RCDK won't work.
Wait, expansive or compressive?
You lose information in the sense that I don't know about if it's expansive or compressive. It's when you do the decoding, because when you do the first layer, you're doing compression. You lose some information in your compression. So your compression is always lossy. It's just how lossy your compression is. Yeah. Does this make sense? Yeah.
What is the time constant in terms of units here?
So it depends on the device. So this device,
Okay, slow time down.
yeah, so I can choose the time constant. You see that this is the decay, it's not exponential. Okay. Anyway. So this is a stretch exponential fit. Yeah.
Is there a way to influence that time constant? Yes.
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 Yes. You can build different devices. Yes. Yes.
On the same device, can you influence?
It also depends on the pulse amplitude. So that's why you can use the same height, but if you use a different amplitude, you can get more nonlinearity.
And how controllable and reproducible is
This
it?
is very controllable.
So that's not,
Very reproducible.
if I can fill in a gap here, a bunch of us are interested in state-based models for
I
language.
mean, I think it's very reproducible because it's a bulk property. You know, it's a bulk
It is bulk,
property.
yes,
of the-
yes.
of the Devices.
Yes.
Doesn't depend on the detail.
That's right.
structure.
Yes.
It's just simple. Right?
Yeah.
Did you ever try kind of jittering the spikes and seeing what happens or dropping randomly few, how much does it affect your results?
We haven't done that. No, not experimentally. No. All right. So, but we did try other tasks. Okay. This is a more complex task. This is like a time series prediction. Okay. So this is like instead of doing simple classification, you predict the next step, then you use the next step to feed to the same network. Okay. So you do some learning, and then for example, chaotic system, you can't really learn the function. It's deterministic, but it's too complex. You don't know the underlying function. So, but you can emulate, right? So the idea is that you train the network, then you try to emulate the function afterwards over time. Okay. So you generate the next step, you feed it back. Now we don't feed any actual data. We just use this network, try to emulate the actual signal. Okay. But time series prediction is harder. The harder it becomes, the longer you try to predict, because the error grows exponentially, right? So this is basically Mackie glass is a chaotic system. When the tau becomes larger than some number, we actually can predict it to some distance in the future. Again, it's because this network is not simple RC delay. It actually has a very broad spectrum. It actually has learns a lot more frequencies than just a simple RC. Yeah.
Just have a theoretical question. There's a paper that came out at the beginning of this year from a bunch of people, MIT, Caltech, and what all this Kolmogorov-Arnold networks. They really seems like they exploit the nonlinearities at the synaptic level. Does this relate to that, or is it?
Yeah, so we did try RC delay. It doesn't work in this case, okay, because it only has one frequency.
Anyway, the topic, when do we stop?
In about 5 minutes.
5 minutes. Okay, I'm almost done. So this is another example. So you can use devices with very, very low amplitude that can be programmed. You can have devices that can be programmed with 100 millivolts. So that's really potential you can try to connect with biology, right? This is a simple example showing device respond to 100 millivolts pulses with different states, and you can do this kind of prediction. And now we're actually working with real folks who can have these probes. They can have these very nice probes. This is Professor Liu's group at Harvard. They can this very nice flexible flow probes. You can inject really literally using a syringe, inject into animal brain, and the array will stay there very stably for weeks, and they can pick up individual neuron signal for weeks. Okay, very stably. So we use this to do some very simple processing, hopefully on the chip. So this is like you can actually pick up which neuron is most important through some ablation in our network. So I will not have time to go into the detail here, and it's also not completed because we haven't completed study yet. But that's one direction I feel very interested in using this reservoir computing system. So another one is state space model. Okay, so this is exactly you guys are talking about. We are also working on state space models, and they are nice because they are not relying on convolutions, right? They are not relying on convolutions. They are fully compatible with computing memory architecture, and they have some dynamics we can implement. So this is basically one project. We have a first generation of architecture done, but I will be very happy to discuss more, and hopefully we can come up.
Is that spike based? I guess it is spike based.
It's spike based, yes, spike based, completely spike based, yes. So obviously a lot of people here know state space models. You can basically they generate to recurrent convolution or an even transformer type of model, right? So it's very good performance, and also in my opinion, and like Jason and Emery said, it's very, very well suited for computing memory. So that's one area we are very interested, very strongly. Right. I'll stop here.
I'm going to be the. Thank you for giving any questions from the audience?